Today in these notes we are going to see the method of separation of variables. So let's start with a short review of what we saw. Back in lecture 3 we talked about partial differential equations, how to classify them, if they were linear, the order, the dimension, all these features that the partial differential equation can have. As an example, we saw the one-dimensional wave equation, which is here. We have this equation with the second derivative with respect to t of u equal to a positive constant c squared, and the second derivative of u with respect to x. And we have this domain, this interval in x from 0 to L, and t is a positive number. We can think about the t as the time. Okay, so usually we will have a partial differential equation, boundary conditions, and initial conditions. This will be the three ingredients that we will have working in when we are working with partial differential equations. Okay, so here in this case we have these boundary conditions: u at 0, t is equal to 0, u at L, t is equal to 0 for t greater or equal than 0, and these initial conditions, u at x0 is equal to f, the derivative of u with respect to t at x0 is equal to xi, where we will see these functions f and xi, what they satisfy. Okay, so if you remember back in that lecture, we claim that these two families of functions, this un and bn, the names don't matter, but remember that at that point we just said, okay, these two guys, sine of n pi over L x, cosine of n pi c over L times t, and same, but instead of cosine we just put sine in the part of the t. We claimed at that point that these two families are solutions for each value of n, like n equal to 1, 2, 3, and so on. Okay, so today's goal is to justify that these guys that we claim at that point they are solutions. How do we get these two families of solutions? Okay, so that's the goal of today. So at that point we just mentioned these two type of solutions, and we said, okay, these two families are solution of the PDE and the boundary conditions. Remember, this is the PDE, these are the boundary conditions. Okay, and we have these solutions for every value of n equal to 1, 2, 3, and so on. And we know that this partial differential equation is linear, so any linear combination of solutions is also a solution. So we conclude that the most general solution of our partial differential equation and the boundary conditions was given by this candidate ux of t, where we are combining, remember that this sine multiplied with this cosine was the first family of solutions, and the same sine times this other sine was the other family of solutions. So what we are saying here is that, okay, any combination, any linear combination of these two types of solutions that we found would be a solution. And then, okay, we are taking as many as we can, in the sense that, okay, we just sum infinity of these candidates of solutions. And we just suggest this as a general solution. But remember that this candidate came from verifying only the partial differential equation and the boundary condition. And we still need to check that we also verify the initial conditions, which were given here in this example with this function f and g, okay, with u at x0 and the derivative with respect to t of u at x0. So once we take our candidate here and set t equal to 0, what we get is only this part survives, because cosine of 0 is equal to 1 and sine of 0 is equal to 0. So we have this first information that f of x, which is the initial data, one of the two initial conditions, has to be equal to this series that we have here. Then when we see the second initial condition, we have to take this guy again, our candidate, differentiate it with respect to t, and after that set t equal to 0. So if we do that, what we get is exactly this identity. We have g is equal to this is our initial condition, and once we compute this partial derivative of our candidate and then set t equal to 0, we get this expression here. Okay, so now if we remember that we studied Fourier series, here we have let's say something related to the Fourier series with only sines instead of having sines, cosines, and the constant coefficient around. So that would be related to our method of separation of variables to find finally the solution. Recall that our candidate u, which is here, we know everything about our candidate apart from these two guys, which are, well, many of them. They are constant, so we still don't have a solution. This is still a candidate of solution. So to determine finally the solution, we need to find these coefficients that here I call dn and bn, but you can put any number, any name you want. Okay, so we will be able to find the solution of our PDE plus the boundary conditions plus the initial conditions when f and g admit a Fourier series representation involving only sines, because this is what we get when we check the initial conditions for this candidate u. Okay, and this is the main reason why we studied periodic functions, Fourier series, even and odd functions, half-range expansions. So we know that if f and g are 2L periodic odd functions, then we will be able to determine the coefficient dn and bn and finally get the solution ux of t. And that would be the strategy that we have to follow. So Now it's time to see how we get those solutions un and bn, because back to the previous lectures, we were just saying, well, you can check that these guys are solutions of the equation, but how can we get those solutions? And this is when this method appears, the method of separation of variables. Okay, so let's take a look at the method, how to apply the method. As usual, we will have several steps. So we have the first step, separating variables in the partial differential equation and boundary condition. So as the name of the method suggests, is like we have to separate the variables, okay? So that would be the main strategy of the method. What do we mean with separate the variables? We look for a solution, a non-trivial solution, which means we don't like the solution equal to 0. So we look for a solution uxt of the form x, capital X of x times capital T of t. And this is exactly what we mean with separate variables. So this is our original function, u of x t. But we say, okay, I suggest that this solution has this particular form, x of x and t of t. Okay, capital X and capital T. So having this product makes things much easier. We will see in 1 second. So the advantage is that now we have this function x only dependent of x, and the other function t only depending on t, like small t and big T. And this is exactly separate the variables, okay? Now the problem is reduced to finding x and t, capital X and capital T. So plugging this candidate u into our PDE, what do we get? So far, we can already see that this is quite similar to the method of the characteristic equation. In which sense? Because we suggest a particular form for the solution, and then we force this candidate, this suggestion, to really be a solution. And how do we force that? Just taking this candidate and plugging it into the PDE, okay? In that sense, this is quite similar at the beginning of the when we are applying the characteristic equation method. Okay, so here we have our candidate, which is this product of these two functions, and we take our candidate and put our candidate in the equation, plug the candidate into the partial differential equation, which means here we have the second derivative with respect to t of u, which translates in this guy. X stays exactly the same because it doesn't depend on t. And we have the second derivative of t. And here we have exactly the opposite. T stays the same, and we have the second derivative of x, capital X. Okay, and now if we work out a little bit with this identity, we can put together all the information that we have for x and put together all the information that we have for t. And we have this constant c squared that we can put it anyway. I choose putting here in these sides with t, but can stay in any place. Okay. So now that we have this identity, we notice that this side only depends on t, and the other one only depends on x. So the variables are literally separated. And since these variables t and x are independent of each other, the only way to get equality here is to have the functions on both sides constant and equal. that means that we have some certain constant k, which is called the separation constant, such that these two guys, the one side of the equation with the information about t, and the other side of the equation with information about x, both sizes are equal to this constant k. Okay, so now we rewrite the two separated equations as two ODEs, and this is the first advantage that we have here, because we start with a partial differential equation that in principle we don't know how to solve. So we propose this particular solution, this particular form of the solution, separating the variables, and finally plugging this candidate into the partial differential equation. What we get is two different separated ODEs. And the good news is that we already learned how to solve some ODEs in the first lecture. So we are reducing the problem of solving a partial differential equation to solving ODEs, which we already know. And this is usual in mathematics. Try to recycle the knowledge that we already have to solve a new problem. So that's what we are doing here with the separation of variables, with the method of separation of variables. Okay, so these are our two equations, one for x and one for capital X and one for capital T. And as we said at the beginning of the first step, we need to separate variables. The first step consists in separating variables in the partial differential equation and the boundary conditions. So we need to do that now. We separate variables also in the boundary conditions. These two guys were our boundary conditions. So now we plug our candidate, which was x, capital X of x and capital T of t. So we have this other expression for the boundary conditions. And now we look at this guy, T of t, capital T of t, and we can assume that this guy is not exactly 0, because otherwise we would get, we are starting already with the trivial solution, and we don't want the trivial solution. So we can say, okay, look, t is not 0, so I can divide by this t. And what we get finally is these two boundary conditions for the equation of capital X. Okay. So now, as we said, we arrive at this equation for x, at this boundary problem for x, capital X. This second order ODE with constant coefficients, because remember that this k is constant. We don't know the value, but it's constant. And we have these boundary conditions. Okay, so our second step of the method of separation of variables is to solve the separated ODEs that we got in the first step. We have this ODE for x and the other one that we have a bit earlier in the notes for t. Since we have more information about x, we will start solving this equation. Because for t we don't have boundary conditions. So let's start with the equation with the ODE where we have more information. So in this case, it's the one with x. Okay, so we don't know the value of this separation constant k, so we have to analyze all the possibilities. And the possibilities are these three. Our constant k can be positive, can be negative, or can be 0. And we are covering all the possibilities for k with these three cases. When we have k, when we have that k is a positive number, we can rewrite k in this way. Then you will see why it's convenient to do this. But now just believe it, because it's also true. I don't know, you can write 4 as 2 square, right? Or like 5 equal to the square root of 5 square, okay? So any positive number, you can write it in this way for certain mu. Positive, also the mu. And okay, we have the negative case and 0. Here there is a small exercise. The case k equal to 0 will be an exercise, and you will see that you get the trivial solution, the solution equal to 0, and we don't want that. We are looking for non-trivial solutions. So here in the notes, we will discuss these two other cases when k is positive or negative, and k equal to 0 is an exercise. Okay, so let's start with k positive. As we said, we can rewrite k as this positive number mu square. So the equation becomes this, the second derivative of capital X minus mu square, capital X equal to 0, and our boundary conditions. So we solve this second order ODE with the characteristic equation method. Why? Because we can, right? It's a method that we already knew from the first lecture, and we are in the right situation because we have a linear ODE, homogeneous with constant coefficients, so we can for sure apply this method. Okay, so that method was started in this way. We suggest this exponential as a solution where we don't know this lambda value of lambda. But okay, we propose this solution and see what happens. So we plug this candidate into our ODE here. And what we obtain is this equation, lambda square exponential lambda of lambda x minus mu square exponential lambda x. Again, since we know that this exponential is never equal to 0, we can divide by this exponential. So what we get is finally the characteristic equation associated to our ODE, which has, in this case, two real different roots, mu and minus mu. Okay, so we know from all that we did in the first lecture that this we have these two solutions, exponential mu x, exponential minus mu x, and the general solution is just any linear combination of these two guys. Okay, perfect. So we have a candidate for x where we have this C1 and C2, but we also know that this equation, we started solving this equation, the equation for capital X, because we have the ODE and the boundary conditions. So now we have to see if we can find this constant using the boundary conditions. So that would be the next step here. When we use these boundary conditions, we get this system. So look, when we put small x equal to 0, which would be here, we would get this C1 plus C2. And then when we set little x equal to L, here in our candidate, what we get is this other line. Okay, so the first equation gives us this relation between C1 and C2. And the second one, if we replace this information in the second line, in the second information that we have here, what we get is this. Then we have this C1 as a common factor. And when we have a product equal to 0, that means that one of these factors has to be 0. So if we look at the first case, C1 equal to 0 implies, because of the relation that we have, that C1 has with C2, that C2 is also equal to 0, but that would give that x, the capital X, is 0. So we would get the trivial solution again, and we don't want a trivial solution. We are looking for a non-trivial solution. So we don't want this. So what should happen is that this guy has to be 0. But okay, when we solve this, when we work out this equation, what we find here is that mu has to be 0, which is a contradiction because we know that mu is positive. We are in the case that k is positive and k is equal to mu square. So this means that this k cannot be positive, in the sense, okay, if I allow k to be positive, I will get only the trivial solution, which we don't want. So that's why we don't care about the case k positive. Okay, so let's see what happens with k negative. Okay, we can write any negative number as minus mu squared with mu positive. Think about, I don't know, minus 4. Then we can write minus 2 squared, or minus 5. Then we can write minus square root of 5 squared. So we can do that with any negative number. Okay, so in this case, the equation for capital X becomes this one that we have here. And we still have the boundary condition. So again, we need to solve this linear ODE, which is homogeneous and with constant coefficients. So we can use again the characteristic equation method, and then just arguing in the same way. Here you can complete the details later. We would get this the characteristic equation associated to this ODE, which is this one here. So this equation has these two complex roots. And if you remember from lecture 1, that means that these two complex guys, the roots, give these two real solutions, cosine and sine of this mu x. And again, we know the form of the general solution. Then the general solution is given by any linear combination of these two guys, the cosine of mu x and the sine of mu x. And again, we will determine these constants C1 and C2 with the boundary conditions. So when we replace the first boundary condition, we get that C1 is equal to 0 because sine of 0 is 0, cosine of 0 is 1, so we get C1 is equal to 0. And then we replace L, when we use the second initial condition, boundary condition, we get this other identity here, C2 sine of mu L is equal to 0. Again, when we have a product equal to 0, that means that one of the factors has to be 0. So we have these two cases. Let's see what happens if C2 is equal to 0. Then we would get X, capital X, all the time 0. And we don't want the trivial solution, so we don't care about this case. Then what should happen is that this other factor, sine of mu L, has to be equal to 0. Okay, but we know how this function is, the sine. We know that the sine of mu L, or the sine in general, vanishes when we are in these two blue points, when we are in any multiple of pi. And here is the magical moment where this n variable appears, because this function sine has many, like infinitive zeros. Okay, so what has to happen is that this mu L has to be equal to n pi for any n. Okay, so here we have here what we find is the value of mu, which means that we find the value of k, because k was equal to minus mu squared. Okay, so we have for each n a different mu, so a different k, which is n pi over L. So finally, for the equation of x, capital X, we have all these solutions. Any constant, C2, that can also depend on n, and sine of n pi over L x. Okay, for convenience, we will fix this constant C2 to be 1, and we save this information. We find this x, capital Xn, this sine n of pi over L of x. Okay, so the step 2, if you remember, was solving the separated ODEs that we got in step 1. So far we solved the one for x, capital X. And we found also the possible values of k, because we found the possible values of mu. So now, with this extra information, the value of mu, we go back to the equation for t and try to solve that equation. Okay, so the equation for t is here, is the second derivative of t minus k c squared t equal to 0. We replace the value of k, which was minus mu squared, so that's why here we have a plus. And we have even more information because we know that mu is n pi over L. So we put all the information here in the equation and we solve this equation. Again, we are in a second order linear homogeneous ODE with constant coefficients, so we can use again the characteristic equation method, which you already know is suggesting a solution of this type, the exponential with the lambda that we don't know, and proceeding in the usual way with the characteristic equation method, we get to this characteristic equation for the ODE of the function capital T. And this equation has two complex roots, n pi c over Li and minus this one, okay? And we know that when we have two complex roots, the solutions, the real solutions, are these two guys, cosine of n pi c over L times t, and sine of the same argument. Okay, so for each value of n, what we get is this solution for this shape of solution for t. So Tn, capital Tn of t is this combination of cosine and sine of this argument n pi c over L t. And these constants c1 and c2, they can vary with the n also, because for each n we can have these different constants. So finally, if we put together all the information, oh, well, no, not yet. So this constant can also change with n, so we put some names, for instance, bn and dn. You can choose any name you want for this constant. Okay, so now we solved the two separated ODEs because we already know capital X of n and capital T of n for any n. And now we remember, we recall that our candidate was this uxt equal to capital X of x times capital T of t. So we found these solutions, un, which is the product of these two guys that we just found, capital Xn and capital Tn, which are here. This was Xn and this is Tn. And now we know that this is a solution for our two separated ODEs. Sorry, for the general partial differential equation with the boundary conditions. But as we were using always, since our equation is linear, we can take any combination of these UN functions, any linear combination of these functions. So as we said, this UN is a solution of the PDE and the boundary conditions, both. So now, our final candidate is this UXT equal to this any linear combination of the UN x of t, which here you don't see an extra constant because in some sense the constants are already included here when we take this any linear combination of solutions. Okay, and now we are in condition to go to the final step of the method, which maybe you can imagine. We already have a candidate that solves the partial differential equation and the boundary conditions. But we have a third ingredient, which are the initial conditions. So the third step is just using these initial conditions. Okay, how do we use them? Okay, step 3, Fourier series solution of the entire problem is the final step. So the last step consists in determining the coefficients Bn and Dn so that the function, our candidate uxt, verifies the initial conditions, which was, okay, ux of 0 should be equal to f, and the derivative with respect to t of u in x0 should be g, equal to the function g. Okay, these are the two initial conditions. And we have two initial conditions and two families of coefficients to be found. So that makes sense. Okay, so first we use this first initial condition, which is just taking our candidate and set t equal to 0. So when we do that, sine of 0 is 0 and cosine of 0 is 1, we get this guy. F of x is equal to this series that we have here, and it's not a coincidence that has this shape, like with signs of some argument. Okay, so if you remember from when we saw Fourier series, we know that for a function f of x defining on the interval 0L, we saw that if we consider the odd extension of f on the interval minus LL, then we get the half-range sine series expansion of f, which is exactly what we have here. So, therefore, the constants Bn that we didn't know are the sine coefficients of the half-range sine series expansion of f, which we know that we have a formula for that, which is given here, where the p that we usually have in previous lecture here is equal to L, and we have this expression. Okay, that was using the first initial condition. Let's use the second initial condition, which uses the derivative with respect to t of u. So we take our candidate, we differentiate with respect to t, which you already know that this is done term by term. So we didn't care about this guy because it doesn't depend on t. So we have to derivate this guy, differentiate this guy. So this is a constant, that's why it's still there. And the derivative of this part is here by the change of rule. And the derivative of this guy is here. Look that the coefficients Dn are still green because it's what we have to find. We already know these coefficients Bn. Okay, so once we have the expression of the derivative of u with respect to t, now we set t equal to 0. When we do that, again, since we are working with sine and cosine functions, it's easy to compute this because we know that sine of 0 is 0 and cosine of 0 is 1. So what we get is this expression for g. Okay, so it's quite similar to what we got previously for f, with these signs with the same argument. And here we have this dn n pi c over L. So let's change the name of this this purple circle, let's say, and we call this all this number Bn star. Then what we have there is something like this. Gx is equal to this Bn star sine of n pi over Lx. Again, as before, this is the half-range sine series representation of g. For the function g defining on this interval 0L, we consider the odd extension of g in this interval minus LL, and then we know that we have a half-range sine representation of g in this way, where we know how to compute these coefficients Bn start, which are here with this formula that we have here. Okay, so now Bn star was an auxiliary name, right? We are looking for this Dn, but this Bn star was exactly this quantity, Dn n pi c over L. So the only thing we have to do is just work out this identity just a bit to get the expression of this Dn. And that's what we have here. So, conclusion. To solve this PDE with these boundary conditions and these initial conditions, we used a method of separation of variables, which was basically 3 steps. The first step was assuming that the solution has this shape, capital X of x times capital T of t. Plug this u into the partial differential equation and the boundary conditions, both. In the first step, doing this, we will get 2 separated ODEs. And then the second step is solving the separated ODEs that we got in the step 1. And finally, using the initial conditions, the first step is using the initial conditions to determine the coefficients that we get in the second step when we have the final candidate of solution. Okay, so summarizing this UXT here, the series of sine n pi over L x and this other guy depending on t, with this constant Bn and Dn, where we know Bn has this form and Dn has this other form, is the solution of the partial differential equation plus the boundary conditions plus the initial conditions. Okay, in what follows we will see some examples and again how to use the method of separation of variables to find solutions of partial differential equations.